Hello everyone. In this video I'm going to be talking about a type of differential equation called a Cauchy-Euler equation. And in this video, after I discuss what a Cauchy-Euler equation looks like and how the solutions can be found, then we'll just go into some examples of solving homogeneous Cauchy-Euler equations. All right. So first, what is a Cauchy? What are these Cauchy-Euler equations? Well, they're just any differential equation of the following form, or that can take the following form. So all these a sub n minus 1, a sub 1, a sub 0, those are all constants. And it's just like your typical linear nth order differential equation, where I have the nth derivative of y with respect to x, the n minus first derivative of y with respect to x, all the way down to the first derivative of y, and then y itself. But this time, as opposed to previous videos, all the coefficients are not constant. Right? The coefficients include a power of x. And it's specifically set up, right? These Cauchy-Euler equations are very specific in that the nth derivative of y is going to have the nth power of x. Right? So the degree on x is the same as the order of the derivative that it's the coefficient for. And the n minus first derivative has, x to the n minus first power attached to it. The first derivative has x to the first attached to it, and then the the zeroth derivative, right, just y itself, has x to the 0 or 1 attached to it. Pardon me. And then we have equals and then some function of the independent variable, g of x on the other side. Now, like I said on the beginning of the top of the video, I'm going to be focusing in this video on solving homogeneous Cauchy-Euler equations, so this will be 0 over here. Alright, so to solve these Cauchy-Euler equations, at least the homogeneous versions, start off with letting y equal a power of x. Alright, so when there were constant coefficients, we let y equal, some exponential function, e to the mx. Here, when the coefficients are these powers of x, the way to go about solving these is going to be to let y equal a power of x itself, x to the mth power. Then you take a bunch of derivatives, however many you need, right, depending on the order of the equation, substituting it in and simplifying, and you're going to create what's called the auxiliary equation for this differential equation. Sometimes it's referred to as the characteristic equation. And then you're going to solve this, and it'll be a polynomial equation in M. And I go over the few scenarios you're going to come across, or at least in the examples that I'm writing up in this video. So if you find any distinct real roots, right, if you find any roots that are different and real, then a linear combination of x to one of those roots plus x to the other root, so c1 times x to the m1 plus c2 times x to the m2, where c1 and c2 are constants. This expression will be part of the general solution to that homogeneous Cauchy-Euler equation. Now, if you have any roots that are repeated, if, say, m is a root with multiplicity k, then c1 x to the mth plus c2 x to the mth, but then times the natural log of x. So to create newer, k independent solutions to the differential equation, you take this x to the mth and keep multiplying by the natural log of x. And I'll show you how why this is with a different kind of substitution later, but for right now, just when you have a multiplicity of k, you'll have x to the mth times the natural log of x, x to the mth times the natural log of x, to the second, all the way down to x to the mth times the natural log of x, to the k minus first power. And linear combination of those will be part of the general solution to the homogeneous Cauchy-Euler equation. And then the last scenario is if you have any roots that are complex conjugates, right, have a real part, say, called alpha, and an imaginary part beta, right, so alpha plus beta I, alpha minus beta I, suppose those are roots, complex conjugate roots of the auxiliary equation. Well then, x to the alpha times the cosine of beta times the natural log of x, right, all this inside the cosine. This would be one solution to the differential equation, and then a second independent solution would be x to the alpha times the sine of beta times the natural log of x. And then, any linear combination of those will be part of the general solution to the homogeneous Cauchy-Euler equation. All right, so just keep referring back to these if you wish, the different scenarios. And again, I'm going to go over 3 examples where each of these happens at least once. All right, so let's look at an example of a Cauchy-Euler equation. And it's homogeneous again because this function on the other side is just 0. And I guess I should write up that these are, Cauchy-Euler, and hopefully you can see that based on the form I had up earlier, right? You see I have the second derivative has the second power of x attached to it. And then the 0th derivative, y itself, has no x. So this is, and it's all the y stuff's on one side, 0 on the other. So this is a homogeneous, what they would say, a Cauchy-Euler equation that is, second order and linear. So since I recognize that, this equation is a homogeneous Cauchy-Euler equation, I'm going to start off by letting y equal x to the mth power of x. And then, dy dx, or y prime, would be m times x to the m minus 1. And then I'm second order here, so I got to go to the second derivative. The y double prime would be m times m minus 1 times x to the m minus 2. And then when I substitute, let's put sub. When I substitute these expressions into the equation, we get, the following. We have x squared times, m times m minus 1 times x to the m minus 2 minus 2 times x to the mth equals 0. All right. And then what we get here is m times m minus 1, then minus 2, right? And both of these terms would have x to the mth power in common. Well, x to the mth power is just y. And, this is a homogeneous equation, right, as I've mentioned. This is a homogeneous equation, meaning that y equals 0 is a solution. Right, that's the case for any homogeneous linear differential equation. So if we focus on we're going to focus on the functions y that are not always 0. We're going to focus on y not being 0. So if that's the case, then y is not 0 all the time. I can divide by y, and we get what's called, again, the auxiliary equation for this Cauchy-Euler equation. And that would just be this polynomial equation m times m minus 1 minus 2, equals 0. Just dividing through by x to the mth, or dividing through by y. And this is a quadratic equation here, right? This is m squared minus m minus 2 equals 0, and find the roots. Now you could use the quadratic formula, or complete the square method, or this one in particular, this example is pretty easily factorable. We have m minus 2 times m plus 1 equals 0. All right, so the roots, I'll call them m1 and m2. I could replace m with 2. I could also replace m with negative 1. And so I have that first case that I mentioned earlier in the video. We have some distinct, different, real, no imaginary part. We have some distinct real roots. And that means that, replacing m with 2, m with negative 1, that means y equals x squared is a solution. And you can verify that. Also, y equals x to the negative first is a solution, and you can verify that as well. And if that's the case, also any linear combination of those is a solution. So what I like doing, and you've seen me do this in previous videos if you've been watching my videos, I'll put that fundamental set of solutions, which is just a list of the basic linearly independent solutions to the second order equation. Now it is a second order equation, right? So I should be finding 2 independent solutions, and they're here, right? X to the second and x to the negative first. And you can use the Wronskian if verify that these two functions are linearly independent for x not 0. Right. And then finally we can state the general solution. Would be y equals, and then any linear combination of these two. So say c1 times x squared plus c2, constant c2 times x to the negative first, where c1 and c2 are constants. Okay. And I would leave it to you to verify this. I would leave it to you to verify this. Just take the first derivative, take the second derivative of this expression, and substitute it into the equation, and you would see indeed we'd have a true statement, right? And like I said, I'll leave that to you. All right. Now that is one way of going about solving a Cauchy-Euler equation. An alternate method is to transform a Cauchy-Euler equation into a linear equation with constant coefficients through a simple substitution. And this substitution will do that transformation for any Cauchy-Euler equation. So an alternate method of solution is to transform the Cauchy-Euler equation, CE for Cauchy-Euler, into an equation with constant coefficients, which again we know how to solve from earlier. An equation with constant coefficients. Now how do we do this? Pardon me. You make this substitution. Replace not y, but replace x with and then you introduce a new variable t, or some other new, whatever other variable you wish. It doesn't have to be t. So replace x with e to the t, or you could say t equals, the natural log of x. They're the same statement. All right. And what's going to happen here? All right. So here's the original differential equation. It's x squared times, the second derivative of y with respect to x at the moment. But what I'm going to do is write things in terms of this new variable t. I'm going to treat the new variable t as the independent variable. And then we have minus 2y equals 0. All right. So first off, if I want to replace the second derivative of y with respect to x, with another expression involving derivatives of y with respect to t, I'm going to use the chain rule. All right, remember dy dx. So y depends on x, and x depends on t now, right? Because I'm making this substitution, would be equal to dy dt multiplied by dt dx, right? Through the chain rule. So y depends on x, which also depends on t. So y depends on t, and t depends on x this way. And what is dt dx? All right, dt dx, the derivative of t with respect to x, is just the derivative of the natural log of x is 1 over x. So this is 1 over x times dy dt. Right. So that would be an expression I'd use to replace dy dx with something involving dy dt. But I want the second derivative of y with respect to x being replaced with something. So following this statement, the second derivative of y with respect to x, and then I would have to use the product rule here. So that'd be the first 1 over x times the derivative of dy dt with respect to x, then plus, and then dy dt times the derivative of 1 over x. But the derivative of 1 over x is negative 1 over x squared. Right? That's x to the negative first, and you're talking with respect to x. All right, and then I can go through here, right? I can use the rule I just wrote, right? The derivative of some function with respect to x is 1 over x, times the derivative of that function with respect to t. So this would be equal to 1 over x times, and then this, according to the previous line, would just be 1 over x times the derivative of dy dt with respect to t. So that'd be the second derivative of y with respect to t, right? The derivative of the first derivative of y with respect to t would be the second derivative of y with respect to t. And then I have minus 1 over x squared times dy dt. All right, now I have an expression where the second derivative of y with respect to x is in terms of the derivatives of y with respect to t. That's 1 over x squared times the second derivative of y with respect to t minus the first derivative of y with respect to t. And look what happens when I make this substitution into my original differential equation. So if I sub this, put this in place of the second derivative of y with respect to x, see the x squareds would cancel, and I have the second derivative of y with respect to t minus the first derivative of y with respect to t, and then minus 2y equals 0. And what I have now changed it to, and again, this will happen for any Cauchy-Euler equation when you make this substitution of x equals e to the t, or t equals the natural log of x. What I've done is I've turned it into a differential equation now, a linear differential equation with constant coefficients, but it's in terms of t instead of x, right? The independent variable is now t. All right, and we know how to solve these, right, from previous videos. And you're going to notice that I'm going to end up with the same solutions as I got with the first method. Remember, I let y equal some exponential function, right? E to the mt, right? Don't forget the independent variable is t now. And then we get the auxiliary equation. Let's put aux. It'd be m squared, right? M squared minus m minus 2 equals 0. And oh look, it's the same solutions as earlier. We got m minus 2 times m minus 1, or sorry, m plus 1 equals 0. So my roots are 2 and negative 1. So the general solution of this equation, where t is the independent variable, is y equals some constant c1 times e to the 2t plus c2 times e to the negative t, and then don't forget that t was the natural log of x. So now I go back, I sub back, and we get the solutions of our original equation. Y equals c1 times e to the 2 times the natural log of x plus c2 times e to the negative natural log of x, right, replacing t with the natural log of x. And this is c1 times x squared, right, using properties of logarithms. And the log of x squared, and then the e and the natural log would cancel. Same thing here. Plus c2 times x to the negative first. And this is exactly the same solutions, exactly the same general solution as I wrote up earlier. All right. Obviously, it just that takes longer. All right. Although now that I have what I would substitute for the second derivative of y with respect to x and the first derivative of y with respect to x, that'll make the next examples easier to do with this alternate method if you wish. So again, I'll do it both ways. All right, I'll do it both ways. All right. So next example. So another homogeneous Cauchy-Euler equation. And you see how the second derivative has x to the second attached to it. The first derivative has x to the first. And then the 0th derivative, the original y, has no x. And it's homogeneous again because you got 0 here. So if I recognize, hey, this is a linear, homogeneous Cauchy-Euler equation, that first method would be to, let's just let y equal some power of x, right? X to the mth. And then going through the same procedure as before, my auxiliary equation, I'll just put, again, aux, would be m times m minus 1 in this second derivative area, plus 5m, right? M would just be in the first derivative area, plus 4 equals 0. Because again, when I substitute y prime, y double prime into this, every single term would have x to the mth or y in common, and we're going to ignore the y equals 0 because y equals 0 is a solution all the time. Okay, and then again I have second order equation has a second degree polynomial auxiliary equation. This would be what, m squared minus m plus 5m would be plus 4m, then plus 4 equals 0. This is again nice and factorable. This is just m plus 2 squared. So what I have here for my roots, m equals negative 2, but it has a has a multiplicity of 2. It's a repeated root. With a multiplicity of 2. So when I go to write the fundamental set of solutions to this equation, right, the two linearly independent solutions to this, when I go to write the fundamental set, it'll contain x to the negative second, right, replace m with negative 2, and then x to the negative second, but then times the natural log of x. Right. There's your two linearly independent solutions to this differential equation. And then any linear combination of these would form the general solution, right? So the general solution of this equation is y equals, some constant c1 times x to the negative second plus some other constant c2 times the natural log of x times x to the negative second, and where c1 and c2 are any constant. Right, and again, obviously x can't be 0, so maybe you'll go for x greater than 0, x less than 0. Well, actually, it's got to be x greater than 0 if I'm doing natural log of x. But I'm not going to worry about writing that right now. Now you can verify this. Again, I'm not going to do it, but you take the first derivative, take the second derivative, plug them in, and you'll indeed see that the equation would be true. Right? This two-parameter family of solutions do satisfy this differential equation. Now again, I'll go through the alternate method. All right. So again, that alternate method, ALT, where you replace, instead of replacing y straight away, you replace x with e to the t, meaning t equals the natural log of x, same thing. And as I wrote up before, I'm not going to do the whole thing again, but dy dx would then get replaced with 1 over x times dy dt. And the second derivative of y with respect to x, which is y double prime here, would be 1 over x squared times, and then the second derivative of y with respect to t minus the first derivative of y with respect to t. Right, I found these on in the first example. So we make these substitutions. So subbing all this stuff involving t, I'd have x squared times y double prime. So the x squared would cancel. So I have the second derivative of y with respect to t minus the first derivative of y with respect to t, right, in the first term there, plus 5 times, x y prime. Well, x times y prime, the x's would cancel, and y prime is replaced with just, dy dt. So plus 5 times dy dt, and then plus 4y, so plus 4y equals 0. Now, do you see how this is y double prime, where, again, this is with respect to t. Right, the independent variable is t now. Not x. So I have y double prime plus 4y prime plus 4y equals 0. And I let, now I have a differential equation with constant coefficients, right? All those x squared, x are gone, right? So in that case, I let y equals e to the, the mt, get the auxiliary equation, m squared plus 4m plus 4 equals 0. So again, the roots would be negative 2, but with a multiplicity of 2. Let's say negative 2 repeated. And so the general solution of this equation would be y equals, some constant times e to the negative 2t plus some constant times t times e to the negative 2t, right? If you remember when you had repeated roots of these equations with constant coefficients, right? You just had e to the one exponential and then it again with powers of the independent variable attached to it. And then I sub back. And we get the solutions of the original equation in x. Y equals, some constant times e to the -2 times the natural log of x. Remember, t was the natural log of x in my substitution earlier. Plus some constant c2 times the t is the natural log of x times e to the -2 times the natural log of x, and both of these are just x to the -2nd. c1 times x to the -2nd plus c2 times the natural log of x times x to the -2nd, and I get exactly the same general solution I got earlier. All right. So again, yes, it is a longer method, but you end up with the same result. All right, substituting all this junk, right? Making sure you keep that in mind. But still, another way of doing these Cauchy-Euler equations if you wish. All right. All right, so I've had an example where we had two different roots. Had an example where we had a repeated root. So I got one more example here of another Cauchy-Euler, homogeneous equation where the independent variable is x. And then I'm hoping I picked the right. I picked an example where I'm hoping I think that the you're going to get that third case where you have the complex conjugate roots. So again, I recognize, hey, this is Cauchy-Euler, right? Y double prime has x squared attached, y prime has x to the first attached, y has no x attached, and 0 on the other side. It's homogeneous. So just like the other two examples, I'll do it the quick way first. Y equals x to the mth power. And then after doing the first derivative, second derivative, and subbing, we get our auxiliary equation, which will be 3 times m minus 1 in the second derivative slot, plus 6 times, and then just m in the first derivative slot, plus, and then just 1, right, the coefficient of y there. And I divide it through by x to the mth, right, or divide it through by y. And it's another quadratic. This would be 3m squared. Then minus 3m plus 6m would be plus 3m plus 1 equals 0. Okay, now again, you can solve with the quadratic formula. I personally like completing the square. So this is divide everything by 3. You get m squared plus m, subtract a third, and complete the square, right? Half of 1 is a half, squared is a fourth. So add a fourth to both sides. Now, putting these together, this is -4/12 plus 3/12. That's -1/12. Right. And then this side here is m plus 1/2. Quantity squared equals -1/12. And so we have m plus a half is positive or negative. Square root of a negative is going to have I attached. I times the square root of 1/12. Now, the square root of 1 is 1. So we have I times 1 over the square root of 12. And the square root of 12 simplifies. So I times, and then 1 over. Now, square root of 12 is 2 times the square root of 3. And then if I rationalize, multiply the top and bottom by the square root of 3, we get plus or minus I times the square root of 3 divided by 6. All right. So my roots, solving for m here, I'll call them m1 and m2. Well, let's say m equals. And just write them as a conjugate pair with the plus or minus. We have -1/2, right, subtract 1/2, plus or minus, and then the square root of 3 divided by 6 times I. Right. So I have the scenario now where my roots are complex conjugate pairs. And in that case, we just had to identify the alpha and the beta. Alpha was the real part, negative 1/2. Beta was the imaginary part, is this square root of 3 over 6. Right, and then I'll write the fundamental set of solutions, right? The two basic linearly independent solutions to this equation then. If you remember what I wrote, or go back to what I wrote about this scenario with the complex conjugate roots earlier in the video. So one solution to this equation would be x to the alpha, x to the negative half, times the cosine of beta square root of 3 over 6 times the natural log of x. And then the other linearly independent solution is x to the alpha, x to the negative half, times the sine of beta square root of 3 over 6 times the natural log of x, all of this inside the sine there. So I've got my two linearly independent solutions, and you can verify, take the first derivative, second derivative of this, plug it in to the equation, you'll see the equation is true. Same thing for this one, and then any linear combination of these would also be a solution. So the general solution here is y equals some constant c1 times x to the negative half times the cosine of the square root of 3 over 6 times the natural log of x, right? So plus some other constant c2 times x to the negative half times the sine of the square root of 3 over 6 times the natural log of x. And there we go, right, where c1 and c2 are any constants. Okay. All right, and then just as with the first two examples, I'm going to go through an alternate method. That alternate method where I let replace x with e to the t, or t with the natural log of x, and again, the first derivative of y with respect to x, y prime, will be replaced by 1 over x times dy dt. The second derivative of y with respect to x, or y double prime, will be replaced by 1 over x squared times the second derivative of y with respect to t minus the first derivative of y with respect to t. Now I'll tell you right now, we'll get this equation. So subbing becomes this. Now again, the independent variable is t this time, right? Independent variable is t and not x. And we get an equation that would basically look just like that would lead me to the same auxiliary equation. Right? I'll have 3 times y double prime, where this is with respect to t, plus 3 times y prime, which is with respect to t, plus y equals 0. And then I have now an equation with constant coefficients, so we let y equal e to the mt, get the same auxiliary equation, right? 3m squared plus 3m plus 1 equals 0. The roots are m equals negative half plus or minus the square root of 3 over 6 times I. It's the same root, same auxiliary equation here. And hopefully you recall then, the general solution will be y equals some constant c1 times e to the negative half t times the cosine of the square root of 3 over 6 times t, plus, and then some constant c2 times e to the negative half t times the sine of the square root of 3 over 6 times t. And then if you just let t, right, remember that t is equal to the natural log of x, put that into this, you're going to get my solution from earlier back after simplifying. It's exactly the same thing, replacing t with the natural log of x and then rewriting stuff. Okay? So yeah, so again, if you know what you're doing, that alternate method could be pretty quick. But if you if you recognize that, hey, this is an Euler equation, a Cauchy-Euler equation, because it's got that special form, and just make that substitution. Hopefully you remember all the scenarios. What does the general solution look like when the roots are distinct, when they're repeated, or when they're complex conjugates. All right. Again, if you don't remember that, maybe you should do the alternate method. Make these substitutions here, and then get an equation in terms of and solutions in terms of t, and then put natural log of x back in for t. All right. So I hope watching me do these few examples help you out when you're solving your own homogeneous Cauchy-Euler equations. And thank you very much for watching.